Welcome to this Cambridge Alumni Festival talk on cosmic creations by Professor Roger Davies, who's the Philip Wetton Professor and also Director of the Hinsey Centre for Astrophysical Surveys at the University of Oxford. I'm really pleased to have been asked to give a quick introduction and also to tell you about two tours that Roger and I are involved in. My name's Ed Payne and my company, Last Frontiers, has been running alumni tours for Oxford and Cambridge for some years now. We're a specialist tour operator to Latin America and Antarctica, and I was lucky enough to take part in a very memorable trip with Roger as trip scholar when we went to Chile to observe a total solar eclipse in 2019. We tried to repeat the experiment in late 2020 when another total eclipse crossed Argentine Patagonia, but we were scuppered, I'm afraid, by COVID. That tour eventually developed into an astronomy and wine trip, which is running from the 15th to the 27th of November this year. That's the leaflet on your screen. We've got 10 participants. We're visiting vineyards around Mendoza and in Patagonia, and Argentina's main astronomical observatory in the Andes. I may be able to accept one more couple. So if you'd like details, please just send me an email. My details are on the screen. For eclipse fans, the next total eclipse in the Americas is in April 2024. And Roger and I are planning an alumni tour to see it. While the eclipse path crosses the entire continent, the best chance of clear skies is in Mexico. And our tour will also include some Aztec observatories, and we hope the main Mexican observatories, which are near Puebla. The final itinerary should be ready in a matter of weeks, and I'll offer places in the order that inquiries are received. So feel free to send me an email, again, to that email on the screen to register your interest. Now, I'd like to welcome Roger Davies to talk to us about galaxies and many other things, I'm sure. I was lucky enough to hear him talk on several occasions in Chile, and know it will be a fascinating presentation. Please do add any questions via the Q&A button at the bottom of your screen. I will do my best to summarize them and put as many as we have time for to Roger at the end of his talk. Thank you very much. Roger, over to you.
Thank you very much, Ed. I hope you can now see my screen. There we go. Okay, hello everybody, and it's my job this evening to talk about how galaxies are made, and I've divided this talk into sections where I'm going to talk about a little bit about cosmology, so that's the starting point, what we start off with, and then I'll talk about the end product, so I'll tell you a bit about galaxies, what we're aiming to make, and then we'll cover the ingredients, so dark halos, cosmic collisions between galaxies and black holes, and then we'll put those ingredients together in a recipe and see if we can make some galaxies. And right at the end, I will give you some of the latest ideas that have come forward from the James Webb Space Telescope. So here we go. In the beginning, 13.8 billion years ago, there was the Big Bang, and it really was the beginning. It was the start of space and time. These sorts of pictures are very misleading. It always is presented as if it was an explosion. That's not really an appropriate image, but of course an appropriate image will be very difficult to make. So we're just going to start with the Big Bang, and we're going to give ourselves 400,000 years of time to generate this. So this is the cosmic microwave background. It's a cool plasma, 2.3 degrees Kelvin, so very cold. And what you're looking at here is a picture of the whole sky taken from space using the European Space Agency's Planck satellite. And this is basically just the surface of the plasma that cooled from the Big Bang. And what you're looking at here are very small changes in temperature across the sky. The changes are a few parts in 100,000. So very, very tiny changes in temperature from one part of the sky to another, represented by these blue and red speckles. And corresponding to the changes in temperature, there are changes in density. So some parts of the universe at this very early time were just very slightly more dense than others. And this is absolutely crucial for forming galaxies because, of course, gravity is a single-signed force. It's not like electromagnetism, where like charges repel and unlike charges attract. Galaxies, gravity, mass, always attracts to other mass. And so if you start with a little bit of the universe that's slightly overdense, that part of the universe will be a little better at attracting the mass around it, and that overdensity will grow. And over time, this positive feedback produces the structures in the universe that we see today. And so I want to show you now an old computer simulation from my colleagues in Durham, led by Carlos Frank. And this is a simulation of matter. It's dark matter, but we'll come to that shortly, which is only affected by gravity. So the only force at work here is gravity. So let's run this simulation and see what happens. So this is the cosmic microwave background time. And as you can see, those little density fluctuations have grown really quite dramatically. And they grow very quickly. There's a clock down in the bottom left-hand corner there. We're almost up to the present day here. So you can see here, we've gone through the whole history of the universe in those few seconds. And the simulation is now rotated. So you can see the cosmic filigree, what we call the large-scale structure, the filaments, the clusters at the nodes of the filaments, and the empty voids in between. I think we'll run that again, just so people can watch it. So here we are. This is as if it were the cosmic microwave background. The small density fluctuations are amplified by gravitational growth, and the dark matter clusters to form what we call dark halos, which are the sites of galaxy formation, as we will see. And in between, not only do we see the places where galaxies form, but we see this large-scale structure that I referred to. So dark halos merge together, making ever more massive halos. Okay, so what is actually made in these halos over time? If we look around the universe today, what do we see in terms of galaxies? So here are some pictures on the lower part of this slide showing what galaxies look like. These are not typical galaxies. These are usually quite big galaxies. But if you look at the properties of galaxies as a whole, the masses vary a lot. You could have galaxies that weigh just 100 million times the mass of the sun, a mere 100 million times the mass of the sun, up to 1,000 billion times the mass of the sun. So these are huge objects. The diameter can be a few thousand light years across to 200,000 light years across. And here are our ingredients from which galaxies are made. So you can see the stars. These are photographs of the stars in galaxies. There is neutral and ionized gas in them. So you can see some of the gas in these spiral galaxies, and on the left-hand side here, this beautiful radio galaxy. You can see dust because you can see that, that there is sort of dark lanes superimposed on some of these galaxies, and that is what astronomers call dust. It's more like cigarette smoke than the dust you find under your bed, but you know, it obscures the light beyond, so it makes these characteristic lanes on the images. And then, of course, a very important ingredient, dark matter. Okay, so let's start with the ingredients for making galaxies. So the first one is dark matter, the dark side of galaxies. So look at the photograph of this group of galaxies in the left-hand side of this screen. That is the Ursa Major group in the Big Dipper, in the Plough. One of the closest groups of galaxies to us, and there are three galaxies here. A big galaxy, M81, a little galaxy M82, excuse me, and a tiny galaxy here that doesn't have a Messier name. And this photograph that you see here is in optical light, and it's a negative photograph, and it's showing us where the stars are. And the impression that this gives is of isolated galaxies separated by quite large distances. In fact, of course, galaxies used to be called island universes. In the middle of the screen, there is a beautiful picture of the same group of galaxies in the same orientations. You can see where they are, but this is in the light of the radiation given out by hydrogen gas. And this gives a completely different impression of this group of galaxies. You can see, first of all, that it looks like the galaxies are all connected in terms of neutral hydrogen gas, and they're very much bigger. You can see the galaxy in the middle here is very much bigger in hydrogen gas than it is in stars, and the galaxies give the impression of a turbulent, interacting group. So that's one thing, the galaxies are bigger. The other thing, of course, remember that the universe is expanding from the Big Bang, and that means that these galaxies, and all galaxies, were closer together in the past than they are now. So what that means is that the tidal effects between galaxies are going to be much stronger in the past than they are now. Okay, so this is nothing to do with matter. So let's think about dark matter now. How do we measure the masses of galaxies? So on the left here, there's a schematic of the solar system. And if you measure the velocities of the motions of the planets around the sun as a function of their distance from the sun, this is what you find. Of course, nobody will be surprised to know that Mercury, the winged messenger, is the fastest. And as you move further away from the sun, the velocities of the planets decrease. And they decrease by a law set by the universal law of gravitation, which tells us that the velocity of the planets falls off like 1 over the square root of the separation between the sun and the planet. And that's what you see here. So as you move away from the sun, its gravitational influence declines, and the velocities of the planets also decline. And this is a characteristic setup for a point mass at the center with essentially tracer masses out at large radii. Now, on the right-hand side of this slide, you can see a spiral galaxy. And we can use the neutral hydrogen gas, the hydrogen gas in this galaxy, to trace out the velocity of the gas in the same way as a function of radius away from the center of the galaxy. So here's the center of the galaxy, and this is what we see. So here we've got a plot of the velocity against the distance from the center of the galaxy. And we can work out from this picture what we expect that curve to look like on the basis that all the mass that's there is what we see in the light. And when we do that, we expect to see this blue curve here. That's what's expected. When radio astronomers go out and measure the velocity of the hydrogen in this galaxy, what they find is this curve here. So in other words, instead of declining like this, which is a bit of a similar curve to this, you can see that the velocity of the gas is much higher than expected. And this is telling us that the matter in that spiral galaxy is extended, and is extended and very much larger than the optical image of the galaxy. So you can see here that in the middle of the galaxy, the light that we see, the disk of the galaxy and the bulge in the middle, accounts for much of what we see in terms of the velocity. But as we go further and further out, there's a component which we call dark matter, which is required in order that the galaxy won't just spread out and disintegrate, that the gravity will hold the galaxy together. Now, this is telling us there's a huge amount of unseen mass in the outskirts of galaxies, which we call dark matter. And although we don't know what dark matter is, and clearly that's a major problem, we have lots of independent sources of evidence showing us that it exists. I won't go through all these, but the first indication we had that there was dark matter in the universe was in clusters of galaxies, where the individual galaxy velocities were so large that if the only mass present was what you see in the light, the clusters of galaxies would disperse quite quickly. And so this was always a puzzle. Why are there these rich clusters of galaxies that we see around the universe? What holds them together? And this was called missing mass originally. We now call it dark matter. There are lots of other bits of evidence to show this. The only slight wrinkle on our confidence that we do have dark matter is, do we really fully understand gravity? If our theory of gravity is wrong or needs modifying, perhaps there's something a little bit more to this story than that. But we have a lot of tests of that, and we're pretty confident that that gravity, our theories of gravity, are correct, and dark matter is a very important part, very important constituent of the universe. Okay, so let's move on to our second ingredient for making galaxies, and that is cosmic collisions. So these are amongst the most spectacular things that we can see in photographs of galaxies. Here are two galaxies. Here's one, here's the other, merging together. They are beautiful. There are some wonderful examples. And one of the telltale features of the tidal interaction between galaxies where they are merging is shown here in the bottom left. You get these long tidal tails, which are essentially orbital resonances. The stars are thrown out on a particular path. This object in the top right here is the result of a bullseye collision. The galaxy, one galaxy has passed right through the middle of the other one, and it's produced an expanding ring, which is of slightly denser gas, and in that denser gas, stars are formed and produce this beautiful ring galaxy. So, colliding galaxies are relatively rare in the nearby universe. We don't see a lot of them, but because galaxies are closer together in the past, and because we now understand that they have much greater masses in these dark halos than we ever envisaged before, as we go to earlier times in the universe, so more distant away from us, Hubble Space Telescope has shown us that merging galaxies are much more common in the past than they are today. Now, here's a feature of galaxies which we need to understand and make some kind of explanation for, which mergers will help us with. So on the right here, there are these beautiful pictures that you see of the Catherine wheel shaped spiral galaxies, and they go from some lovely face-on examples here in this column to some edge-on examples on the right-hand side here. And these galaxies, these type of galaxies, spiral galaxies, are consistent with all being very flat disks. So as you see on the right-hand side, and the only difference between them is that some of them are looked at face-on and some of them are looked at edge-on, but they're all thin disks. On the left-hand side, we see much less spectacular images. These are sort of star piles. On the left-hand side, they just look like blobs. On the right-hand side, they look like edge-on blobs. They clearly have a disk, these ones on the right-hand side. But if you look at the same way at the distribution of the shapes of these galaxies, these objects are not consistent with all being the same intrinsic type of shape. And the ones on the left-hand side here are shaped very much like a potato or a kiwi fruit. They have three different axes, and they, generally speaking, do not have a disk of stars in them, and the ones in between are in between. But the key point here that I want to get across to you is that these spiral disk galaxies are forming stars. All these little knots here in the disks are all regions that are forming stars very energetically. There are a lot of stars forming in these spiral galaxies. Whereas on the left-hand side, in the so-called quiescent galaxies, they're quiescent because they're not forming stars. So there's a connection here between what the galaxies look like and whether they're forming stars or not. And that's something that we have to understand and explain in our theories of how galaxies form. And the key ingredient here is what happens when galaxies merge together. And so what I'm going to show you now is a simulation of what will happen to the Andromeda Nebula, which is our nearest galaxy, and that you can see on an autumn evening, and not quite yet, but soon you'll be able to see it with the naked eye. It's the faintest thing that you can see with the naked eye. If you're in a good dark site, you have to be in a very dark place, and you've got to let your eyes accommodate to the darkness. So you can see the nearest galaxy. This simulation is going to show us what happens when the Andromeda Nebula, which is another spiral galaxy, and the Milky Way, what happens to them in the future. So let's run the simulation. Okay, so here it is. Here's the Milky Way with its central bar and its spiral arms. You can see rotating here, and the camera will zoom out, and into the bottom left-hand corner will come the Andromeda Nebula, M31, and its companion, the neighbor galaxy in Triangulum, Messier 33. And the orientation now just switches around to show us that when M31 is edge on, the Milky Way is not. And so the orientations, these are not in a single plane. Now, here they are, first pass. Gravity is not strong enough to capture them. They escape from each other on the first pass. But as they fall towards each other for a second time, gravity's relentless action causes them to merge together into a single object. And this is the fate of our own Milky Way with M31 many billions of years in the future. And you can perhaps look out here for some of the very faint features in the outer parts of this galaxy, which has resulted from the merger of M31 and the Milky Way. And what you find is that they form an object which looks just like a quiescent elliptical galaxy. And when we look at those kinds of galaxies, quiescent galaxies not forming stars, then this is what we often see. So if we take very deep pictures, we see these shells around early type galaxies. Here's a very spectacular example. And these low surface brightness shells are the remnants of some of the particular orbits in the spiral galaxies that went into a merger. But what happens in the merger is not just that the two galaxies coalesce, but this is a very violent merger, this one, and all the gas between the stars is disrupted and it's heated up, and all the star formation is caused to cease during the merger. And so this is how we make a connection between the structure of the galaxy that we see and whether it's forming stars or not. Now, we can look at our own Milky Way, and this is a complex but beautiful picture. We've had a satellite flying now for a decade or so called Gaia that has measured the positions and velocities of the stars in the halo of our own Milky Way galaxy. And it's been possible for people to identify stars that have a common origin because they have a common they're made of the same stuff. They have a common constituency. And these arcs here show us the star streams that result from the many accretions, the many acquisitions that the Milky Way has had over its lifetime. So the Milky Way is quite a massive galaxy, but it's grown over time from many acquisitions and accretions and coalescences. So not dramatic coalescences, but gentle coalescences that allow us to trace the past history of the satellite objects that have merged with our own Milky Way to form it in the way it is today. And so here's a schematic that shows that over time, you find these, we identify these wisps of stars and star streams falling that represent the past of what were star clusters and dwarf galaxies that have merged with the halo of our own Milky Way. So I want to leave you with the picture there that some mergers can be violent, such as the one I showed between the two giant spiral galaxies. But in assembling our own Milky Way galaxy and in more isolated systems, you can have gentle coalescences that build galaxies over a long period of time, a little bit at a time. So the third ingredient that I want to draw out in this story is the role of black holes, central black holes in galaxies. And you probably have been familiar with this picture of a black hole in a galaxy that was taken by a radio telescope and published in the last 2 or 3 years. I'll tell you how that came about, but first of all, let's look at the black hole at the center of our galaxy. So here is a very, very wide field view of the center of the Milky Way. And you can see here, this is the size of the full moon. So this is a big lump of sky. This is the bulge of the Milky Way around the galactic center. This is a dark lane that obscures, a dark lane of dust that obscures the galactic center from our direct view in the optical. Excuse me. The center of the Milky Way is about 25,000 light years away, and it is hidden from us at optical wavelengths by this obscuring dust in the plane of the disk of the Milky Way. Now, I'm going to show you now a simulation, or this isn't a simulation, this is an animation of the measurements of the motions of stars around the center of the Milky Way that have been taken over the last couple of decades. And this is a remarkable experiment because it records both the positions of stars and therefore over time we can measure by taking a picture each year, we can see how the stars move around the center of the Milky Way. And these images that have been used have been taken at infrared wavelengths, which pierce the dust. The infrared radiation can make it to us from the center of the Milky Way, so we can see the motions of the stars. And I'll run the animation now. So these measurements were taken by a couple of groups, one in Germany led by a scientist called Reinhard Genzel, and one in California by Andrea Getz. And they shared, I'm going to run it again, they shared the Nobel Prize in 2020 for this work. Well, let's actually, we didn't go right back to the beginning, did we? Let's really go back to the beginning. We'll go back, here we go. We'll get it again. Yeah, here we go. So watch again. And in particular, watch the yellow orbit. Look how quickly it whips round that star, which is the center, marks the center of the Milky Way. Here it comes again. It doesn't quite get to the center, but I want to show you the latest data. So this is the latest data taken around 2018 and since. So on the left-hand side, on the right-hand side, you can see the path of that star on the yellow orbit. It's called S2, as it passes from April, May, and June in 2018. And you can see that on the 19th of May, 2018, it was only 120 astronomical units. That's 120 times the distance between the Earth and the Sun, away from what we call Sagittarius A, the radio source that marks the center of the Milky Way. This is a plot of the velocities of the stars, of the star as it went round. And when you correct for the inclination of the orbit, you see that this star, when it's closest to the center of the Milky Way, is moving at 7,600 kilometers a second. That's an extraordinarily quick motion. And it's telling us that there's a very large mass enclosed within that orbit. And this is actually showing you the orbit. So this is the position on the sky in 2 dimensions. This is 416 here times the, distance between the Earth and the Sun. And we've only been able to do this because we can measure the positions of the stars 1 year after another and build up a complete picture of the orbit. The mass that's implied by these motions using the same the same technique that we use to measure the mass either of the sun or of the spiral galaxies, is 4 million times the mass of the sun. Now, we can look further afield and look, this is a galaxy in the center of the nearest cluster of galaxies, the Virgo cluster, and it's known as Messier 87. And there's a black hole in the center of this galaxy. And this is a picture of the black hole in the middle of this galaxy taken by the Event Horizon Telescope, which I'll tell you more about now. So here is the Event Horizon Telescope. Now, it's not a single telescope. It's multiple radio telescopes, about a dozen radio telescopes spread out across the Earth. And the radio signal from M87 is recorded separately at each of the locations of the telescope. So there's a telescope at the South Pole, there's a couple of telescopes in Chile, there's one in Mexico, one in Arizona, a couple in Arizona, one in Hawaii, a couple in Europe, and one up here in Greenland. And the data from these separate radio telescopes is combined to make an image by very sophisticated techniques that would appear, so that it would appear to come from a telescope as big as this circle, so almost as big as the Earth. And looking at M87 in the optical, I've shown you this picture before, you can see it's in a cluster of galaxies. Here are some more galaxies here, look. That's what it looks like in the optical. This is 300,000 light years. If we look at the central 1% of that, 3,000 light years, we see radio emission, and we see this jet here coming from the center of the object, and that jet preserves its angle when we go from 3,000 light years scale to 3 light years scale, down to 0.3 light years scale, and then right down here we see the radio image taken by the Event Horizon Telescope of the radio emission, which is distorted by the black hole in the center of this galaxy. And this gives us an independent way of measuring the mass of the black hole in the center of this galaxy. So here is a blow up of with fewer steps of this system, and we're able to estimate the mass of the black hole in the center of the galaxy from the size of the ring, basically. So the diameter of the ring is d. The diameter of the ring here is 3.8 micro arc seconds, and that diameter is given to us by the gravitational constant times the mass of the black hole divided by the distance to the object divided by the speed of light squared. So since we can measure the size, we know all the other things, we can determine the mass of the black hole. And it turns out that the mass of the black hole in M87 is 6.5 billion times the mass of the sun. So more than 1,000 times more massive than the black hole in our own Milky Way. Okay, so let's now put all these ingredients together and see what the recipe is for making galaxies. And I want to spend a little bit of time on this schematic. So the brown circle, the large brown circle in this schematic represents the dark matter halo. There's some rotation because, of course, all those halos rub up against each other and they cause tidal interactions, and those tidal interactions generate a little bit of spin. We find gas that cools and falls into the dark halo, and that cooling gas can form a disk of stars because it's got angular momentum, or perhaps if it has less angular momentum, it forms stars in a spheroidal component. But in the disk of stars, we see stars evolving, and the massive stars will explode into supernovae, and the stars that are not quite as massive will lose some of their material out into the gas between the stars and enrich it with heavy elements. So the atoms and molecules that fall into the dark halo, they can cool and form stars in the disk. Those stars enrich the gas by throwing out the chemical elements that they've made into the interstellar medium. Some of that gas is hot enough that it escapes, so the hot gas goes out beyond the dark matter halo, particularly in lower mass galaxies where the dark halo isn't quite as massive. Some of it falls back and makes another cycle of star formation. And as another galaxy falls in with its halo will coalesce with this dark halo. It will disrupt that star formation, alter what the galaxy looks like. So this is the sort of basic model we have for making the galaxies that we see, the stars and gas in galaxies that we see. So I want to show you a simulation now, but from the Eagle team, of both the dark matter, the gas, and the stars as time passes. So you want to look down here in the bottom left-hand corner of this image, because it starts here at 0.2 billion years, 2.2 gigi years after the Big Bang. So that's sort of redshift, for those of you who know about redshift, at 19.8. First of all, it shows us what's happening with the gas. And it shows the temperature of the gas. Oops. Oh, sorry, that hasn't run the. Let's go. Here we go. So at the beginning, we can see the small density fluctuations growing, and the gas is cool. The image is all red. The temperatures are low, but of course, as the gas falls into the dark matter halos, it heats up, and so now you start seeing some regions of the structure that you see that are lighter colors, white colors, and the gas is heated up in these deep potential wells. And as we can now see, look at down the bottom left here, where it's a redshift of 1 now, 5 or 6 billion years after the Big Bang, you can see that the voids are opening up, that the gas is being thrown out into the space between the galaxies, and it's now quite hot. And look at, you can see particularly here on the right-hand side of this simulation, you can see that the gas is thrown out into the space between the galaxies. And now we've reached the present day. This now shows us the cold dark matter, what we believe to be the material that forms the dark halos. And you can see that we're already at a redshift of 5 or 6 here. You can see that forming the large scale structure. We're going to zoom in now and show what happens to the gas and see how a particular galaxy is assembled. And look at the gas, it's pretty chaotic. It's quite a chaotic system. Lots of little bits of gas are falling together. You're beginning to see now that the material has formed a disk, and this is what the stars would look like. So you see there's much more structure, much more knottiness, and much more fragmentation in the gas than there is in the stars that you see. And now you see the gas building up. The galaxy is larger than it was. Big bits fly by like that, some of which are collected and accreted into the disk. So you can see how those star streams would form in the halo of the Milky Way. And now we're looking, it's growing in size, and indeed, here we are, this is what the stars look like. Now, at this point, we can see a limitation of these simulations, because these are cosmological simulations. They show us what the whole cosmos, or a very large chunk of the cosmos, looks like as cosmic time passes. And you need, I'll run that again just so you can watch it while I'm speaking. In order to be able to look at the largest possible scales, our computer simulations are limited by resolution. So you can't look at the finest scales if you want to simulate a huge piece of the universe, as we are doing here. And so if you want to look at how galaxies really do form and what they look like when they've finished forming, what is done is little sections of these simulations are cut out, and they are started again at much finer resolution, so that we can follow what happens in the detail needed to see what individual galaxies will look like at the end of this formation process. And so our computer power is enormous, but it's not great enough to go all the way from the beginning of the universe to the present day with the detail we need to see what happens to individual galaxies, unless we use this technique of cutting bits out and starting them again at finer resolution. And I will show you in a moment a simulation that does exactly that. So we're coming to the end here now. This is what happens to the cold dark matter. And we'll watch the galaxy again, because it is rather beautiful and rather chaotic what happens in the gas. But it leaves a rather simple looking galaxy of stars that's a little bit misleading, because that's where the limitation in the resolution of the simulations comes in. So look at all these small pieces falling into the galaxy and assembling to make a much bigger structure. And there's the stars, and back to the gas. And we'll just go through to the end. So you can see the spiral structures, how the stars naturally find themselves in these structures, these Catherine wheel-like structures. There's a companion galaxy flying by, having bits ripped off it. Some of those bits fall into the galaxy, other bits escape away. So you can see here a very turbulent, dynamic system. And that's what the end product looks like. So, but it's a rather smooth, simple galaxy. So I'll show you something that looks a bit more sophisticated than that in a moment. Okay, now I shall show that in a minute. So one of the great things about cosmological simulations of this kind is we can do experiments. And what I want to show you is an experiment that allows us to see what the effect of black holes is on the formation of galaxies. So when I go back to this, it starts at the beginning of the slide. So on the left-hand side, we'll see what happens to galaxies if there are no black holes in the center of them. And on the right-hand side, we'll see what happens in galaxies that have black holes in the center of them. And again, we're going to look at the gas temperature and density. So the green is the gas density and the red is the gas temperature. Okay, let's run it. So on the left, here we are, you see the same structure forming, right? So the masses are the same everywhere. It's just that on the left-hand side, there are no black holes in the simulations. Look what happens on the right-hand side. The gas is heated up, it's much more spread out and much hotter. We just run it again. So on the left-hand side, you do have gas that's heated, but nothing like as much as you get on the right-hand side, where you get much hotter gas and much more extended gas. So black holes cause gas to be heated and spread out in the large-scale structure, and that's because although the black hole doesn't emit any radiation, the act of accreting all the material around it and generating the jet that you saw in the M87 galaxy, that forms a disk of material around it, which gets very hot, and it generates a lot of radiation. The jet generates a lot of radiation. That radiation and also the kinetic energy that it generates disrupts the other gas in the galaxies, in its own galaxy and in the galaxies around it. And that actually is a contributing factor to stopping the stars forming. So of course, one thing we have to worry about is that if only gravity is occurring here, then why don't we end up just with one big galaxy? And one of the answers to that is that black holes inject a lot of energy and radiation into the gas between the stars and stop that gas cooling and forming stars. So this is a slide that just illustrates what I was saying about taking cutouts from a particular simulation and running them at higher resolution so that you can see what's happening in more detail. This is done in the New Horizons simulation. And the next slide, I think, shows some stills from that simulation, creating a galaxy that's a little bit more massive than the Milky Way, 2 or 3 times more massive than the Milky Way. And this shows us different stages in that process. So at early times, a redshift 4, so many billions of years ago, the Milky Way was very patchy like this, unstructured, no spiral structure. As time passed, it remained like that, but began at a key time around a redshift of 2. It began to get a disk structure. You begin to see something that looks a bit like a spiral galaxy here. As time passes by, it looks more so. And this is at a redshift 1. It looks actually quite like some of the galaxies that we see around us today. I should say that the top images here are the face-on view of this galaxy, and the lower images are the edge-on view. So you can see this has got still quite a fat disk here. It's quite a hot disk. So now I'm going to show you the simulation from which those stills were taken. And this is where you can really see the star streams coming in and see a spiral galaxy like the Milky Way being assembled. Here we go. So here's early times. There is no clock on this, but you can see it's highly chaotic. Things are coming in, disrupting everything. You can see these shells forming that I showed you. Now we're beginning to see a bit of a disk, but lots and lots of small accretions. There was a big event just then. There's another quite large event. They don't really disrupt the whole disk, but they do make it asymmetric. But as time passes, the galaxy grows. It's much bigger than it was at earlier times. And you can see now something which looks quite like the spiral galaxies we see today. You can see the dust lanes. You can see something that really does look like a disk galaxy that we see around us. So let's wind things up here. Galaxy assembly, the recipe. So this is how it works, more or less. Dark halos grow under the influence of gravity hierarchically. So little halos produce big halos produce even bigger halos. Stars form from the cooled gas that falls into those halos and creates the heavy elements. The massive stars do. The massive stars explode as supernovae and spread that material out into the interstellar material and intergalactic material. This is enough to disrupt the star formation in low mass galaxies. But in massive galaxies, it's not enough to disrupt the star formation, and you need the radiation and the mechanical energy from the jets and the accretion disk around the black holes that heats the cold gas and suppresses and ultimately stops the star formation. And of course, what happens to the black holes as the galaxies merge, the black holes in their centers will also merge together. And so you find that the black holes grow in mass at the same time as the galaxies grow in mass. And we refer to this as the co-evolution of galaxies and black holes. And I'm just coming to an end now. I thought, what about what next? I thought you might be interested to see the spectra that from James Webb Space Telescope, which I only saw last week. And so these are spectra from a colleague of mine, Carl Glazebrook, at Swinburne University in Australia. It's a bit difficult to see what you're looking at here, but these yellow lines, arrows, point to places here where there are spectra, the light spread out in the colors of the rainbow. I'll go to the next slide where it's much clearer. So here we see light from 0.8 of a micron to 5 microns wavelength. Spread out, you see 5 little bands here, 5 individual spectra. And in this one, you can see light along one of those bands and 2 bright points. Those 2 bright points are emission lines in a galaxy at very high redshift, not hugely high here. This is a redshift of about 4. And these galaxies, it turns out, are challengingly massive for the models that I've been showing you at these wavelengths, at these redshifts. These galaxies are more or less the same mass as the Milky Way already at high redshift. So they've evolved very quickly. And they're beginning to challenge some of the ideas we have about how galaxies assemble. The other thing that James Webb has come up with, which is highly controversial, are galaxies at very, very high redshifts. That is a controversial result, perhaps still very early days, looking at these kinds of spectra, trying to interpret them. But James Webb will have a lot to say in the future about some of the remaining problems about how galaxies form. So with that, I'll close and take questions. Thank you very much.
Roger, thank you so much. That was absolutely fascinating. We have just got time for a couple of questions, and we have a couple of questions. First out of the starting block was John Smith, who earlier on, I think, asked, into what is the universe expanding?
Well, it's not expanding into anything because, of course, the Big Bang is the start of space as well as time. And so there is no space out there beyond the Big Bang, beyond the universe, as it were. That's a not very satisfactory question, I realize, answer, John, but that's the way it is.
Okay. And Paul Wright has asked you, Roger, why are spiral galaxies spinning, and do quiescent galaxies also spin?
That's a very good question. And the answer is that the spiral galaxies spin much faster. Why are they spinning? That's because the gas can dissipate, what we say dissipate. It can lose energy in one direction, and the angular momentum determines what direction that is. So it starts off with a little bit of angular momentum, just spinning quite slowly. But then the clouds in this disk will interact with each other, and they will lose energy preferentially in the direction that causes them to flatten into a disk, and that causes them to spin up. As they collapse, as the gas gets to smaller radii, it's got to conserve angular momentum. So as the radius decreases, the velocity of spin has to increase, and so that's why they have fast velocities, high angular momenta. If you think about the way in which the quiescent galaxies form through these major mergers, their orbits, the orbits of the disks, are disrupted in 3 dimensions, and so stars are thrown out into all kinds of orbits, and they can't, because there's not very much gas in them, not very much cold gas in them, they can't form any more stars, and so they're just formed into these 3-dimensional shapes, and they have much lower angular momenta, and we can measure that, and that's indeed what we find.
Thank you, Roger. That was great. Well, I think you've certainly given me a lot of questions, but we've got one more question, and we do have time for it. Eric asks, does this analysis help us in the search for life-supporting exoplanets?
Yes and no. Not really is the answer. This is not part of our search for exoplanets. However, it is interesting to know that the Milky Way, for example, obviously any exoplanets we're going to find are going to be in the Milky Way. So it is interesting to know that the stars in the Milky Way were assembled from lots of small satellites, where the stars formed a long time ago in a universe a long way away, as it were. They're in little fragmentary stellar systems. And so, of course, one of the puzzles of exoplanets, and of course, the ultimate question about, are we alone, is that these stars that came in at early times, of course, they formed a long time before the sun. So the sun and the solar system have been evolving the way they are for 4.6 billion years. But some of these very old stars have been evolving for 10 billion years. And so some of them will, they've had a lot longer time to have evolved some kind of biological activity. And so probably a much wider range of stars in old stars, a much wider range of stars are able to potentially host some kind of primitive life than necessarily we would see just in the last 5 billion years. So we have to kind of put some context around our search for example, atmospheres that can support life, realizing that many stars are much older than the sun and will have had much longer to try and do that.
Thank you, Roger. And Barney Harford has asked you, what causes the flares associated with black holes?
Okay, so that is that is the accretion of material onto the black hole. So this requires a little bit of explanation. So the black hole, of course, itself does not emit light. However, it grows because material flows in towards it because of gravity. That material has to lose angular momentum to get close to the middle. It does that by spinning quickly. Right in the middle, near the black hole, there's a disk of material, which the clue is in the name, called an accretion disk. So the material can move from the outer part of this disk to the inner part, and from the inner edge of the disk, material can fall into the black hole, and that's what causes a flare. And so these flares have been seen both in stellar mass black holes and in the kind of black holes I've been talking about here, the supermassive black holes that we find in galaxy centers.
Thank you, Roger. And finally, I think all we probably will have time for, Michael Durr asks, how does dark energy change this picture? Michael, I'm not quite sure what picture you're talking about, but maybe Roger will know.
So how does it change this picture? Well, it changes. So how did it change this picture is really the question, I guess. So in the late 90s, a couple of teams used supernovae as distance indicators to explore the expansion of the universe, trying to measure the rate of expansion, the Hubble constant, and the rate at which it's changing. And when they started the experiment, they were looking to see how the rate of expansion was slowing down, because we felt at that time that the material content of the universe, the mass, would cause the expansion to slow down. And so they were trying to measure something called the deceleration. They controversially at first, but very convincingly, showed that the universe is not decelerating, but it's accelerating. And we give the name to the effect that it's accelerating to be dark energy, which is kind of like a pressure that pushes the galaxies further away from each other at late times. So it is true that the excuse me, the galaxies did slow down, but now they're accelerating away. What this shows us is that in the future, mergers, for example, will become much less common. And so the universe will end it rather quietly and in a cold way, excuse me. And so it's a rather quiet, empty universe at the end.
I think that's a wonderful point. You lost your voice. You've finished off the universe. Anyway, I look forward to hearing more of your tales on a mountaintop in Argentina sometime. And thank you so much for such an absolutely fascinating talk. And I hope everyone involved enjoys the rest of the festival. Thanks, Roger.
Thank you very much, Ed. I look forward to seeing you in Argentina too.